Okay. Good afternoon, teacher, classmates. Today we're going to talk about effort estimation. But what is estimation and why it is so important? Well, the estimation is a process to find the most accurate sizing figure for the software project effort. For example, how many months will be necessary to develop the software, how many resources we will need to finish the project in the required time, and also how to translate all this to money at the end. This is a critical phase in any project planning because it gives the project team some confidence about the required effort and time to plan ahead for the project. Moreover, this estimate will be used as a foundation to negotiate the project cost. Effort estimation represents the third step of the project planning process. Before we can plan the project schedule, we have to estimate the effort and duration of all the work package. Effort estimation will generate a lot more information than only effort and duration. Information like who will be responsible for each work package, what is the work package specification, what are the expected results of each work package, how is the achievement of the results measured, what are the prerequisites for the work package, what are the conditions under which the work has to be done, what are the required start and end times, what and how many material is needed for each work package and what cost, what tools are needed for each work package at what rate, and all that kind of information. Obviously, effort estimation needs expertise on a work package specific level to accomplish this transition. As mentioned before, the estimation is a process, and this process contains the following steps to reach an estimate. This process is cycling until you reach the final estimate for the process. The first step is scoping. First, you need to define and document the estimate expectations. When all participants understand the scope and purpose of the estimate, you will not only have a baseline against which to gauge the effect of future change, you will also head of misunderstanding among the project group and clear up contradictory assumptions about what is expected. The second step is decomposition. In this step, you will need to break your software into smaller components and functions, and you can categorize them to a different set of elements. After that, you have to sizing. Size is generally the most significant, but certainly not the only one. Cost and schedule driver. Overall scope of a software project is defined by identifying not only the amount of new software that must be developed, but also must include the amount of the pre-existing one and other software that will be integrated into the new system. In addition to estimating product size, you will need to estimate any rework that will be required to develop the product. The fourth step is expert review. At this point in the process, your estimate should already be reasonable. It is still important to validate your methods and your results. After an initial estimate, you will need at some point to ask for expert opinion for some new functionalities you might not be aware of. And finally, the estimation finalization. And this can be considered the final step as you aggregate all the estimations from all components and functions and have a baseline estimate. You can go another round across the process until reaching the correct estimate, which will be approved by the project team and the management as well. There are two kinds of approach for estimating the effort of each work package, the deductive and inductive. The deductive or top-down method assume the total cost for the project is given. From there, we assign the cost and thus the effort of individual work package based on estimated percentages derived from earlier similar projects with similar work packages. The advantage of deductive methods is a simple, rapid cost allocation. And the disadvantage is that they only work for projects that consist of work package that we already know from earlier similar projects. And the inductive or bottom-up methods, the basic idea of inductive methods is to start effort estimation with the work packages individually, with support of experts or knowledge of similar work packages of earlier projects, and then summarize bottom-up. There are some inductive or bottom-up methods that I'm going to talk about. First, there is a factor analysis. And here, for example, we have a work package that is influenced by a number of people that is involved in this project, a number of interfaces, and also a number of blocks and functional blocks. From earlier projects with similar distribution, we might know the correlation coefficients. So we know the variables that influence in the work and how they correlate each other. Then we can calculate the effort based on a mathematical formula which reflects that influences and correlations. The second one is multiplication method. Here, if we can divide a work package into a number of equal parts, then we can estimate the total effort by estimating one part and then multiplying this value by the number of parts. Well, the third one is the analogy method, and this method again applies the knowledge from similar work packages. We interpolate or extrapolate the effort for the work packages from a similar one. For example, for the work package of install electrical wiring in an apartment of 100 square meters. We could get the effort by interpolation from similar work for apartments of 150 square meters and 50 square meters. That, for example, the 150 square meters is 10 days and the 50 square meters is 6 days. So the 100 square meters is 8 days. Then the function point method. The prerequisite is that we need to have a lot of knowledge about the effort of work packages of similar scope and degree of difficulty based on observation. Then the experts compile this knowledge into so-called function curves, which we can use to estimate the effort for new work packages. In the following example, we estimate the effort of work about creating 100, 500, and 800 lines of code. We obtain the effort via the corresponding function points of the function curve, 5, 16, and 33 working days, respectively. And finally, the Delphi method, we just ask the experts for each work package for their best guess, normal guess, and the worst guess. Thus, we obtain three figures for the expected effort: the optimistic, the normal, and the pessimistic. Then combine them with the formula, with this formula, and if we can ask then 10 or more experts, we could even calculate the mean values and apply mathematical statistics with the concept of standard deviation.
Okay, now we're going to speak about the paper we chose, that is Ontology-Based Multi-Agent Effort Estimation System for Scrum Agile Method. And the problem that tries to solve the paper is that currently there's no accurate technique to estimate the effort for Agile methodologies. and it says that more than 59% of the projects are delivered late and over budget for these companies that use Scrum methodology. So the principal cause that indicates the paper is that the software companies do not save the information gained from previous projects. This information could help, if we organize it well, to understand the nature of the future projects that have the same nature, that are similar. And also, what happens is that the Scrum Masters, in general, all the stakeholders, in one moment leave the company, and because they leave the company, the information they gain it, the experience, the lessons they gain it from previous projects, live with them. So that's a problem. And the approach that the paper gives is the multi-agent effort estimation system, that it uses the management of the previous knowledge of the knowledge of previous projects through a system of multi-agents, so we can estimate the effort. And how does it do it? How does it do it? We have 5 core components, and the first we're going to see is the ontology knowledge base, that is this model, this Scrum ontology model, that is described in a 5-tuple that are the C, I, P, R, H, R, C. The C is a set of classes that we can actually see in the figure. If you can read it, those are like sprints, developments, testers, all the terms that are used when you all the terms that are used in the Scrum methodology. And we have I, that is a set of instances of or objects that are objects of these classes. Then we have P, that are properties. Well, we can see there that, for example, P1, SPR1, and I4. And this means that the instance 4 belongs to the sprint 1, to the project 1, of the project 1, and so on. We also can see the RH, that are the hierarchy between these instances, and then RC, that are similitudes between these instances. And the main purpose of this ontology model is to organize knowledge, so later we can use our system, multi-agent system in it. Okay, but first we're going to speak about the knowledge creation component. That is basically that we have the stakeholders of the project and the Scrum team, that can be the developers, the analysts, the designers, and they can create and should create instances that they think that are relevant for the estimation of the effort. And then these instances are validated by the Scrum Master. So here we have a graph of instances, and the instances that the Scrum team can create are the lessons, the priority of these lessons, the features that must be included in a sprint, etc. So here we have an example. If we make zoom on one of them, we can see a lesson that is implement and test the financial feature first, and has the Scrum priority high. Then we have the multi-agent effort estimation system. For the explanation of this component, we're going to see the detailed architecture of the proposed approach. So we can see here that the Scrum team creates the instances, the knowledge, and then the Scrum team validates it. If it's validated, then it's added to the ontology knowledge base. And then in order to the system to start, we need the project specifications of the Scrum team. And what are these specifications? This. So we have the software category. In this example is commerce. Then we have relevant projects, top K lessons, lessons priority, and the method we're using. So once we have these specifications, the system can start. The system has 5 agents, and each agent uses a description logic in order to calculate what it needs to calculate, and uses this description logic and is applied by the Hermit OWL. The Hermit OWL is a reasoner that uses ontologies to reason. So you can see that in the description logic we have classes of the ontology we described before. So we wouldn't be able to use this if we don't organize our knowledge in our ontology. So yeah, this is the description logic of the project agent. And basically what it does is at the end is calculate the sprints required in order to complete the project and the length of the sprint. So we can see what each agent gives us. So the project agent, as I said before, gives us the sprint required and the estimated length of the sprint. Then we have the feature agent that gives us the estimated number of features that should be completed under each sprint. These features can be, as I was saying, these features can be like, I don't know, to have a form of registration from the client, no, for the client, to have a connection to PayPal, etc. Then we have the phase agent. A sprint is conformed by phases that are the analysis, the design, the coding, and the testing. And for each of these phases, we need a team and a length. So the system gives us it gives us the size of the team and the length of the phase. As you can see, we have there 1, 2, 6, and 3. That if we add those numbers, we're going to get 12 days. That is the length of a sprint, of a full sprint. So then we have the lesson agent that is going to give us the lessons that were learned from previous projects that are similar. So for example, here we have in the phase of coding that we should implement and test the financial feature first before anything, and that the priority is high. So at the end we have the estimated effort. Since the agent for estimations need the information of all of these agents. All of these agents work in parallel and then give the information to the estimated effort, to the estimated agent, and this agent will give us the effort in person days. So this is the final interface for the system where we put the requirements and we get an output. And well, we have the knowledge stream maintenance component that is quite simple also. It's just that sometimes for the necessities of the software companies to be satisfied, we need to apply this model of the Scrum ontology we described before, and that can be done. So that is this component is in charge. And the last component is map and integrate project data, and it's in charge of mapping the core elements of tools that are used for Scrum, like Taiga and Orange Scrum, and well, to map them to the knowledge classes of the Scrum ontology model. So it can be easy for current software companies that are using Taiga and Orange Scrum to migrate the information of those tools to the multi-agent system. Well, the validation of the approach. To validate the approach, it was put together a team of 7 professionals that were 3 developers, 1 analyzer, 2 designers, and 1 engineer quality. And all of them had more than 2 years of experience. And the approach was compared with 2 widely used techniques, like are the planning poker and Delphi. And we can see here the numbers now. We can see the magnitude of the relative error. And well, actually, this table gives us more information. I mean, analyzes the last table and gives us the estimation accuracy. So we have that the proposed approach is 91% of accurate, and the planning poker 83%, and the Delphi 75%. So we can say that the proposed approach is more effective in order to estimate. And also another conclusion is that, well, we wouldn't lose our information, no, because we need to, in order to use this approach, we need to organize it well and save all the information we think is relevant. So we will also, if we use this approach, we will also save important information for the future. Thank you.